Hello, everyone. We are going to discuss the next chapter, which is finding the electric field using Gaussian theorem. So I'd like to summarize what is actually the comparison between the chapter 5 and the chapter 6. So let's start with the chapter 5. Sorry. So in the chapter 5, we need to calculate the sum of the integral from the Coulomb's law, which is based upon the force between the Q1, Q2 and R1 to scale to unit vector. So that if you have a Q1 here and Q2 there, and this is R1 vector, this is R2 vector, it's R1 minus R2 vector. And we call it, its magnitude is going to be R12. Okay, that's the notions. And then in order to do that, we applied this law such that from this one, we found out that E is given by Q times 1 over 4 epsilon r scale at the point charge at origin. And then this is the zero dimension, and then zero dimension. And then we apply this to the one-dimensional case. This is the line charge with the line charge density, which is Q by L. And then we have also thought about the ring charge. And then we have thought about surface charge density. So in this case, we also think about lambda Q or pi r. Okay. So this is the surface charge. With surface charge density. And then in this case, in all of the case in the chapter 5, what we have to do is that we specified what the dq is. Okay, so let's assume that like this. It's not the dq. And then we are going to do the integral for the dq. Okay. That's the basic stuff. But the problem here is that the distance between the dq and our observation point P is varying. So we have to integrate all of the things. It may be complicated, and sometimes it may not be integrable. So in comparison to chapter 5, we have a very different case. So it is integration over the dq. Chapter 5 is integration over dq. But in the chapter 6, so we have a Gauss theorem such that E dot dA is Q over in epsilon naught. enclosed. So the integral of the dq is changing into the surface integral. Usually it's a closed surface. So it could be anything like this, and then we have a surface integral of a sphere. And sometimes we have a line charge density, and then we have a cylindrical surfaces. And then sometimes we have, just like the surface charge density, in this case we have some kind of a rectangular box. So our viewpoint is changing. Integral over dq is changed into integral, surface integral, A. Okay. And then from this, we can find out, we can correlate E and Q enclosed. So for the any distribution, so what is important thing is that you take the surface integral, surface, and then you need to find out what is the charge enclosed. Charge enclosed. So it's much more simple. So you know what they are, and then you do the surface integral for the certain symmetry, either sphere or cylinder or a box. And that's the way to tackle the problem. And then in this case, the purpose of the Gaussian theorem is that find E for a given charge distribution. So using surface integral. Okay, so that's the big difference. So in short, in chapter 5, we are going to do the integral of the charge element, but in this case, we are doing the surface integral in the chapter 6 for the Gaussian theorem. Okay, that's the big difference. Okay, let's move on. The electric flux through the square shaped with a given charge sheet is given by E is given, and the flux, electric flux is given. And then it says that the area is parallel to the plate. Find the surface charge density, sigma, on the sheet of charge densities. Okay, so that this is the case. So charge the sheet with the sigma, okay, here. And then note that it is not set in the insulator, it is the conductor, so that we are going to assume that it's insulator. Note that the conductor and insulator has a factor of 2 if 2. Conductor so factor 2 is a big difference, in fact. So here is the case. You need to visualize the electric field that is coming out of this charged plate. And the electric field would be given by sigma over 2 epsilon naught. That means it does not depend on the position. So everywhere is the same as sigma over 2 epsilon naught. And then it is passing through a square area, which is given by S times S. And then this is parallel to the charged sheet. That means electric field normal to is also normal to the this square area. Okay, so note that theta is going to be 0. Okay, and then we need to find out how to calculate the sigma from this information. So electric flux is given, and side length is given. So it means from this we can find out what the area is. And then permittivity in the free space epsilon is given. These two areas are parallel, so that normal vector is same as the normal vector of the charge sheet and the square area, such that the angle between them is 0. And then first of all, we need to find out the area is given by s square. And then we know that electric field is known, okay? And then we have this relationship. And then theta is 0 degree, so that we get E here and then area here. And then sigma is, we can find out what the sigma is from these equations. So flux is known, epsilon is known, area is known. So we can find out the charge density of that this charged sheet. Okay. So now let's try to think about rod. So rod over a radius 3 centimeter, and it has a surface charge density. I'm sorry, it is the linear charge density. Yeah. And then find the magnitude of the electric field at the point of 5 centimeter from the center of the rod. Okay, so that we have this geometry which has a linear charge density, and then what we are going to do is that I'm going to redraw this one. So we have a charge distribution, and then we take the Gaussian surface in the form of a cylinder, and the radius is r equal to 5 centimeters. Okay, and then here is from here to here is the 3 centimeters. Okay. So what we need to do is that do the surface integral and then correlate them to the charge enclosed. So enclosed means is that we have a solution there. So we need to find out the linear charge density, which is given actually. And the distance is given by this one, radius rod is given by, permittivities in vacuum is given like this. And then we note that for the linear cylindrical symmetry for a long straight line, and we know that it is given by this one, and it is simply R. So electric field is on these directions. So electric field is normal to the side surfaces, and then it does not give you any contribution, so that it is the flux. In order to calculate the flux, you need to find out the normal vector, and it is actually making an orthogonal angle to the electric field, so that top and the bottom surface you don't have any contribution, such that if you do the surface integral, you may end up with the 2 pi r times L times E is going to be charge enclosed by this one, which is lambda times L. Okay. So L is cancelled out. You end up with this one. Okay. Sorry, this is. Okay, so that's the thing we already know. And then we get electric field given by this one. Okay. So note that we have used a cylindrical symmetry to calculate the electric field. And then in this case, we have used the line charge line charge distributions. Let me just, okay. Line charge distribution, and then we take the cylindrical Gaussian surfaces. Okay, so that's the key thing you need to remember. And then electric field from the surface. Okay, and then a surface of a ball. So we need to find out electric field is given, and the direction is toward the center, and radius of ball is given. Distance from the surface is given by this one and this one. So in this case, it's a sphere. And then here is the R, which is 5 centimeters. And then we are at the position where the distance from the surface of the sphere. Okay, so it is 10. And then we can obviously we can draw the Gaussian surface, which is a sphere. Gaussian sphere, Gaussian surface. And then we do the surface integral for the electric field, and then we need to find out what is the charge enclosed. So that we need to do the surface integral E through the Gaussian surface. And it should be matched to the charge enclosed divided by epsilon 0. Okay. So in this case, it is the 5 centimeters plus 10 centimeters is our distance. Note that is measured from the center. Okay. And then we note that magnitude of electric field given by Coulomb's law. And then we found out that what is happening here is that so everything inside is now reduced to the point charge at the origin. Okay, so that's the key point of the Gaussian. So whatever it is, it should be shrink into the charge at the charge center, and the total charge is going to be the Q. And then in this case, we all know that what it is. Electric field is. And then we can find out is given by this one. And then we already know what the electric field is. We know what the R is, and then we can find out Q. Okay. So key thing is that whatever the shape is, it reduced to the point charge with the net charge. Okay, so that's the thing. We all know that for the point charge with the radius of r, it is given by this one. Okay. Of course, we can do the same thing. So if you do the surface integral, then this 4 pi r square E. Okay, the electric field would be in the radial direction. And then you should be Q over enclosed, epsilon non enclosed. Okay, so that's same as this one. So I'm just emphasizing once again, you can either derive the electric field from the Coulomb's law by integrating a charge element, but also you can do it with the Gaussian surface integral.